You just brought up noise, and I'd like to get right back to that. But first, since this marks a transition, I suppose, to some of the other content in the Primacy of Doubt, I think I just ought to ask, why did you decide to go from your work in meteorology on uncertainty to tackling all of these other topics like economics, consciousness, creativity, and so on?
A lot of things I do, are not necessarily super logical, but my move into consciousness and creativity actually came straight out of noise, thinking about noise, because having introduced noise into the weather and climate models, and shown that it was beneficial, and it certainly improved the reliability of the forecasts because it had an explicit representation of the uncertainty in the equations, and that helped the probabilistic forecasts become more reliable. But I then started thinking, for years, ever since pretty much the dawn of computing, digital computing at least, it's always been assumed that we want to know the answers exactly. So, if we add 2 and 2, the computer better tell us the answer's 4 and not 3.9 or 4.1. And that's all very well, except that today, with being right at the limit of things like Moore's law and so on, this demand for bit reproducibility in computing systems actually puts an energy overhead on the computer. So I started thinking, maybe we should. Maybe there are circumstances where we can relax this a priori constraint on determinism, bit determinism in digital computers, because after all, weather forecasting is an application where the models benefit from noise. So one way of introducing noise would be to turn the voltage down across the transistors. They'd become slightly noisy. Now, I'm not saying all of transistors, but some of the transistors. And you save energy that way. So you could reinvest that energy by doing more calculations. So it raises the question, if you had a computer where you could, for a unit of energy, do, 1,000 2 plus 2s and get 4, or 10,000 2 plus 2s and get a number between 3.9 and 4.1. What would you rather have? And I was arguing that, at least for weather forecasting, and I can think of a lot of other applications as well, where you actually might prefer more imprecise computations rather than fewer precise computations. But colleagues thought I was completely mad to suggest such a thing, that you'd ever build a computer that wasn't precise and so on. And that's what got me interested in the brain. I was trying to think of, are there physical systems that do this actually in reality? They make constructive use of noise in hardware, not noise in software. Not, the brain doesn't add noise by running pseudo-random number generators. It has noise because it tries to push, electric signals along neurons, 80 billion of them, with 20 watts of energy. And you get thermal noise. You might even get quantum decoherent noise as well. So my interest in the brain literally arose from trying to think about systems in the world where there is noise in hardware, and the brain was one example. But I think actually we're kind of slowly moving. Some of the computer manufacturers are sort of slightly moving in this direction. And I think it'll be interesting in the next few years to see whether this really happens.
Speaking of noise, I recently had Daniel Kahneman on the show, and we spoke about his book with Cass Sunstein and Olivier Sibony called Noise. And that book is more concerned with decisions that groups of people might make. Well, that a judge, for instance, might make the same decision or different when confronted with the same choice, he might make different decisions depending on the circumstances. I think it's less concerned with the individual mind than thinking fast and slow is. But how was Danny Kahneman's work in thinking fast and slow useful to you in thinking about how the brain makes use of noise for creativity?
Well, Kahneman, famously introduced this notion of system 1 and system 2 as two kind of modes of sort of cognitive thinking. One mode 2 being very kind of logical and focused. The sort of thing, when somebody asks you to multiply two numbers together, you'd have to pretty much shut down everything you're doing and focus on that one task, multiplying the two numbers together. Whereas system 1 is probably the mode that we operate in most of the time, where we're not focusing on a particular difficult problem, but just kind of, surviving the world. We're walking around, we're looking around, we're perhaps listening to somebody speak or something. But, it's a kind of multi-purposing process. So that was the first point. And then the second thing which struck me was that when you read about some of the great discoveries that scientists make, and you ask them, where did you make and how did you make this discovery? The thing that gave you your Nobel Prize, for example. As often as not, if not actually more often than not, it was a kind of an idea which kind of came up out of nowhere when the person was just not particularly concentrating on the problem. I mentioned, two people we've already talked about. I mentioned in the book. One is Henri Poincaré, who worked on this the gravitational three-body problem. His key idea was just stepping on a bus one day, and he kind of, oh my God, yes, where's that kind of idea come from? Roger Penrose was crossing the road, dodging traffic. Just the idea came out of nowhere. And it got me thinking, is there any connection between this and this notion that when we're in mode 1, when we're multitasking, this is likely to be the time, I think, when we're most susceptible to the noise in the brain, because this is where the 20 watts are distributed over the multiple tasks that we're having to do when we're in mode 1, as opposed to the single task, multiply two numbers together. All the energy is focused on that single task. You stop what you're doing, you stop walking, you perhaps close your eyes, you put your hands over your ears so you don't get distracted by noise, and just think, what the hell is 19 times 31 or something like that? So these two are very different. And the noise, if the brain's susceptible to noise, it's going to be when it's in Kahneman's system 1. And that seems to me entirely consistent with, the experience of the Nobel Prize winners, that's when they get their kind of eureka moments. And, but of course, the thing is that once they've had the idea, then the deterministic side, the system 2 side, kind of gets to work on it and, really confirms, that was a good idea. That really does pan out. But of course, it's much easier to check. Once you've had an idea, it's easy to check whether it's a good idea or a lousy idea, but it's always difficult to have the idea in the first place. So it kind of struck me that this is a paradigm of creativity that we get ideas out of nowhere from the mode one thinking when we are susceptible to noise. And then we confirm that those ideas are good ideas or bad ideas by going into mode two. And I personally think that, this has not been taken up nearly enough in AI research. This as a kind of mode towards creative thought processes, to actually let the AI kind of just almost come up with, if you like, ideas at random, and then have kind of suitable algorithms for determining whether these are useful ideas or not. In mathematics, AI is very good at checking potential proofs. It will tell you whether it's a good proof or a bad proof, but coming up with the idea is not yet something AI systems can do. And I think that's because the people who develop these algorithms probably don't put enough effort into the potential of just pure noise for generating potential ideas. And I think that is the way the human brain works, pretty much.
You said that when we're multitasking is when we're most susceptible to noise, and I can definitely confirm that from my own experience. It's also when we're distracted, and maybe that is the same thing as multitasking, but also when we're free associating, that's when our creativity comes in. But what I'm wondering is where chaos fits into the picture here and enters the system one thinking in the brain that produces this creativity.
Well, okay. Possibly the answer is this. I don't, not 100% sure, but you see, there are, in a way, and I make this point in the book, there are two types of chaos. There's the chaotic model that Lorentz originally discovered in 1963, which just has three variables. It's kind of relatively easy these days to simulate. Well, it's very easy on a modern computer to simulate Lorentz's model. In fact, you often see in just screensavers, they use Lorentz's model as a sort of screensaver because it's pretty trivial to integrate. On the other hand, you have chaotic systems like the Navier-Stokes equations, which are partial differential equations, which have, well, formally an infinite number of degrees of freedom, so obviously much bigger than 3. I call those high-dimensional systems, high-dimensional chaotic systems. And the reason for introducing noise in a weather forecast model is that the computer is finite, and the computer is trying to represent this infinite dimensional system. So it does it with a finite number of equations plus noise. So the noise is a kind of surrogate for, all the small scale stuff that it can't resolve. And, it could be that that's the way the brain deals with, when it builds a cognitive model of the world. I mean, the world is a complicated, infinite, or for all practical purposes, infinite dimensional system. And, the brain is finite. We have 80 billion neurons. That is a large number, but it's certainly a finite number. And again, the brain, I'm using sort of I'm talking about a part of a human, but I'm using anthropomorphic language to say the brain says to itself, how am I going to represent this infinite dimensional system, which is the world outside me, with my finitely many neurons? And it probably will conclude the best, most accurate way to do that is to represent somehow the dominant structures in an explicit way, and everything that it can't resolve to represent with noise. So I think the way the noise comes about, that will link to chaos, is that noise is a way of emulating in a fairly simple way all those infinitely many degrees of freedom that you can't represent explicitly when your computing system is finite. And in the case of a supercomputer, that's the grid boxes being 10 kilometers or something. In the case of the brain, it's the fact that you've got only 80 billion or so neurons. And so, yeah, I don't know. Does that make sense?
Oh, sorry. It does make sense. And this notion, though, of human creativity, at least on the surface, it appears to contrast directly with another brain and mind adjacent topic that you take on in the book, and that's free will. Because presumably, I mean, if we don't have free will, then there isn't really room for creativity. And granted that, especially when we were talking about quantum mechanics, it became clear that if I understood correctly, that you're committed to a determinist view of the universe. How does everything we've been discussing, I mean, most notably the geometry of chaos, help make sense for you of the puzzle of free will?
Yeah. Well, look, I'm going to give you a partial answer because I don't really claim to completely understand this, but it seems that this goes some way. The issue for me what is difficult about determinism, if you like, is the argument that it lets criminals off the hook. It's the issue about moral responsibility in the world, because the criminal just says, well, I had no choice. What I did, the fact that I killed somebody or I burgled a house or whatever it was determined by the initial conditions at the time of the Big Bang. I mean, I had no option but to do that. So you can't send me to prison because I had no choice. That was what was predetermined that I would do. And I've kind of read a few articles by people who try to, who are kind of avowed determinists, to see how they deal with that conundrum. And I've kind of come to the conclusion that they don't deal with it terribly well. They might say, well, okay, the purpose of sending you to jail is not to punish you, but to deter other people from committing the same crime. I mean, that could be a typical... Or
to rehabilitate you, something like that.
Yeah, okay, possibly. But I feel that's somehow unsatisfactory because, do you let Hitler off just because you say, well, it was all determined by the Big Bang? I don't know. My gut feeling about this is that that you see, I talked to you earlier that this notion of thinking about dynamical systems which evolve precisely on their attractors. In other words, where the equations, the laws are geometric. This is actually quite a different paradigm to the normal, if you like, one in classical physics, where we specify an initial condition and then we have equations which are kind of differential equations which just map that initial state forward in time. And the point I'm trying to make with this picture of the geometry of the attractor being the fundamental quantity is that it kind of all of the points on the attractor are sort of equal ontological significance. There is no kind of initial condition from which everything else evolves. You have to kind of treat. This is why I'm saying it's a kind of a very holistic picture. And I personally think that this is the way in which fundamental physics has to go, and the whole quantum gravity problem, I think, will ultimately kind of come down to the fact that the laws of physics are much more holistic, and, for example, involve the structure of the large-scale structure of the universe as much as, say, just the very small scale, like the Planck scale or whatever. But in terms of free will, I mean, what it means is that the argument that, oh, well, the Big Bang made me do it, this is not a valid argument, because you're appealing to the Big Bang as if it's some special initial state. And in fact, I would say in this context, there's something kind of quite interesting and self-referential in some sense, because I would say that on the one hand, the attractor geometry provides the laws of physics, which determines what individuals do. But equally, what individuals do determines the geometry of the attractor. So there's a kind of a bit of a self-referential loop. And that's exactly the sort of thing, that we see in Gödel's theorem and lots of other really interesting deep theorems in meta mathematics.